Hey everyone, welcome to this explainer. Okay, so today we're tackling something absolutely crucial for civil engineering competitive exams: soil, water, seepage, and flow nets. Whether you're aiming for state or national level exams, this is your complete concept and trick revision guide to absolutely nail this topic.
I mean, if you've ever stood next to a massive earthen dam or a huge retaining wall, you kind of have to wonder, right? How does invisible water actually move around inside the soil? And how does that movement impact the giant structures we just plop right on top of it? Let's figure this out.
All right, here's our game plan. Types of soil water, seepage and Darcy's Law, seepage and uplift pressures, understanding flow nets, and finally, we'll run through some crucial exam questions.
Okay, starting right off with Section 1, Types of Soil Water.
So, when rain hits the dirt, water stores up inside the soil's empty pores. Now, to remember the four distinct types, just lock in this memory trick: GCHC. G stands for gravitational water. That's the stuff just moving straight downward thanks to gravity. H is for hygroscopic water, which is strongly attached to soil particles. It's practically immovable. And the final C is combined water, which is literally chemically bonded to the minerals. You definitely can't budge that one.
Wait a second, you probably noticed I skipped the first C in GCHC. Well, I did that on purpose because this is a massive exam point. That C is for capillary water. This water is held tight by surface tension, and here is the absolute golden nugget for your exams. This is the most useful water for plants, period. If they ask you what plants use, the answer is always, always capillary water.
Moving on to Section 2, Seepage and Darcy's Law.
Okay, so seepage is basically just the physical movement of water trickling through those soil pores. But how does it know which way to go? Well, it's all about hydraulic head. Think of it exactly like electricity. Just like electrical current flows from a high voltage to a low voltage, water does the exact same thing. It always flows from a high hydraulic head to a low hydraulic head.
So let's get into the math of this groundwater flow. This is where Darcy's Law comes in. The formula you absolutely need to permanently etch into your brain is Q equals K times I times A. Let's break that down real quick. Q is your discharge. K is the coefficient of permeability. Little I is the hydraulic gradient. And A is the cross-sectional area. This right here, this is your ultimate equation for solving seepage problems. Let's zoom in on that little I for a second, the hydraulic gradient. It's simply defined as the head loss divided by the length. The logic is super intuitive here. If you have a massive head difference over a short distance, well, that seepage is going to be intense. A bigger energy drop basically means a much stronger push for the water to blast through the soil.
But hey, watch out because there's a huge exam trap here. Darcy's Law comes with one very strict rule. It is only valid for laminar flow. Say it with me, laminar flow. If the water gets chaotic and becomes turbulent, this entire equation just completely falls apart. You gotta memorize that condition. It pops up on engineering tests all the time.
All right, on to Section 3, seepage and uplift pressures.
Now, as water flows, it actually pushes physically against the soil particles. And if that seepage pressure pushes upward, it starts reducing the effective stress. This is what leads to those really terrifying engineering nightmares, like boiling, quicksand conditions, or piping failure right under a dam. It also creates uplift pressure, basically trying to push the entire structure up from the bottom. This is exactly why engineers have to build drainage galleries. You literally have to bleed that pressure off so your dam doesn't just, float away.
Let's shift to Section 4, Understanding Flow Nets.
To actually visualize all this messy underground water movement, we draw these things called flow nets, and they're made of two very distinct types of lines. First, you have flow lines. These just show the actual physical path the water is traveling. And second, you have equipotential lines. These simply connect points that have the exact same hydraulic head or energy level. So the water travels along the flow lines, and as it loses energy, it crosses over those equipotential lines.
And how do they cross? This is huge. They cross at exactly 90 degrees. Honestly, this is the golden angle of seepage. I'm going to say this one more time just for emphasis. Flow lines and equipotential lines always intersect at exactly 90 degrees. They are mutually perpendicular. Write that down because I guarantee you're going to see that as a direct question on your exam.
So why do we even bother drawing these intricate nets? Well, their engineering applications are honestly real game changers. We use them to calculate total seepage discharge, figure out the pressure distribution, pinpoint the hydraulic gradient at any given spot, and calculate that terrifying uplift pressure we talked about earlier. You literally can't design a safe dam or sheet pile without them.
Oh, and a fun fact for you, when those lines cross at 90 degrees, they form these neat approximate little shapes we call curvilinear squares.
Okay, home stretch. Section 5, crucial exam questions.
Time to test what we've learned with a rapid-fire round of previous year questions. First up, out of all the different types of soil water we went over, which one is actually available and most useful for plants?
It's capillary water. Remember our GCHC trick? It's that water clinging to the soil pores via surface tension, making it perfectly accessible for plant roots to just drink right up.
All right, question 2, hitting on the math rules of seepage. Think back to that one strict condition we mentioned. For which specific type of flow is Darcy's Law actually valid? Laminar flow. Awesome job if you got that right. They love to try and trick you by throwing turbulent flow or transitional flow into the multiple choice options, but don't fall for it, it's gotta be laminar.
Okay, last technical question on flow nets. Flow lines and equipotential lines intersect each other at exactly what angle? 90 degrees. They are mutually perpendicular. Keep that golden angle locked in your brain for test day, for sure.
Which brings us to our biggest takeaway. Don't just memorize the definitions. You need to really understand the physical mechanics of why the water moves. Once your core concepts are crystal clear, honestly, the numerical problems basically solve themselves. But before we wrap up this explainer, I want you to think about something. What do you think happens to this incredibly delicate balance of uplift and seepage pressure during a massive earthquake? How do dynamic forces completely rewrite the rules of those flow nets? Well, that is a whole other engineering mystery for another time. Thanks for hanging out with me, and keep questioning the ground beneath your feet.